Alright, let's go. Number 10. The Flatness Problem. Alan Guth was not trying to explain why the universe exists. In 1979, working at Cornell and then SLAC, he was trying to solve a nagging inconsistency in particle physics involving magnetic monopolies. Hypothetical particles that grand unified theories predicted should be everywhere and that nobody had ever found. Standard Big Bang cosmology predicts that the universe's geometry, its overall shape, flat, open, or closed, should drift dramatically over billions of years, moving further from flat with every passing moment, the way a pencil balanced on its tip falls faster the longer it stands. Guth ran the numbers backward, for the universe to be anywhere close to flat today, as it appeared to be. The early universe had to have been flat to a precision of about 1 part in 10 to the 60th power. Not close. Exact, in his 1981 paper Inflationary Universe, A Possible Solution to the Horizon and Flatness Problems, published in Physical Review D, Guth showed that without a mechanism to force this precision, the universe should have either recollapsed within a fraction of a second or expanded so violently that matter could never have clumped into stars. Physicists proposed the geometry was simply a lucky initial condition, but lucky is not an explanation. It's a placeholder for one. Others suggested some unknown symmetry constrained the early universe automatically. No such symmetry has ever been found. Inflation itself, the theory Guth proposed to fix this, requires its own fine-tuned starting conditions to get inflation going in the first place, which physicists sometimes call trading one fine-tuning problem for another. If the flatness of space had been off by even a rounding error at the Planck scale, the atoms that make up your hands right now would never have had anywhere to form. What set the geometry of the universe to that precision, before there was a universe to set it in? That question doesn't go away. It gets worse. Number 9. 3 spatial dimensions. Specifically, Paul Ehrenfest was working on statistical mechanics at Leiden in the 1910s, trying to understand why physical laws take the mathematical forms they do. When he turned to a strange side question almost as an afterthought, why does space have exactly 3 dimensions, and not 2, or 4, or 11? The standard assumption at the time was that dimensionality was a fixed backdrop, arbitrary, unquestioned, simply the stage on which physics happens, with no deeper reason attached to the number 3. Ehrenfest found something the assumption didn't predict. In his 1917 paper published in the Proceedings of the Amsterdam Academy, titled In What Way Does It Become Manifest in the Fundamental Laws of Physics that Space Has 3 Dimensions, he demonstrated mathematically that stable planetary orbits and stable atomic structures are only possible in exactly 3 spatial dimensions. In 4 or more, the inverse square laws governing gravity and electromagnetism collapse into inverse cube or steeper, and orbits spiral either into their central body or off to infinity, with no stable middle ground. 2 dimensions fails differently, nerve fibers can't cross without intersecting, gravitational singularities behave pathologically. And later analysis by physicists including Max Tegmark showed that stable, complex structures capable of processing information may be mathematically impossible below 3 dimensions. Some suggested we simply couldn't observe a universe with different dimensionality because we wouldn't exist in it, which is true, but explains our observation, not the underlying fact. String theorists proposed extra dimensions are real but curled up too small to detect, an elegant patch that has never been experimentally confirmed. Every solid object you touch, every step you take, depends on a dimensional count with almost no room to be anything else. Why 3 out of infinite mathematical possibilities and not some number we'd have no way to imagine? The forces embedded in those 3 dimensions turned out to be just as narrow. Number 8. The electromagnetic to gravity ratio. Paul Dirac was working on the mathematical relationships between the universe's large numbers in the 1930s, chasing a hunch that constants which looked arbitrary might actually be connected by hidden proportions. Physics up to that point treated the strength of electromagnetism and the strength of gravity as 2 unrelated numbers, each measured independently, each free to have been anything at all, with no expectation that their ratio should mean something. Dirac noticed the ratio wasn't just large, it was suspiciously, specifically large, and it matched other large numbers appearing elsewhere in cosmology. In his 1937 paper The Cosmical Constants, published in Nature, Dirac calculated that electromagnetism is roughly 10 to the 36th power times stronger than gravity between two charged particles, a number so large it's difficult to visualize, and he argued the coincidence with other cosmic ratios couldn't be accidental. Physicists have spent 9 decades trying to explain the ratio away. Dirac himself proposed gravity might be slowly weakening over cosmic time to explain the coincidence. Later measurements of planetary orbits and atomic clocks ruled this out to high precision. Others proposed anthropic selection. Only universes with roughly this ratio can form stars that burn for billions of years without either collapsing immediately or drifting apart before life can evolve. Meaning we could only ever measure a ratio compatible with our own existence. That explanation accounts for why we observe it. It does not explain why the number exists to be observed at all. Change that ratio by a handful of orders of magnitude, and stars either burn out in millions of years instead of billions, or never ignite. Every second you've been alive depends on physics holding gravity down by exactly that margin. The margin gets tighter the closer you look at the atomic nucleus. Number 7. The strong nuclear force window. In the early 1950s, nuclear physicists across multiple institutions, including Robert Wilson's group at Cornell, were mapping the strong nuclear force to understand how atomic nuclei hold together against the electromagnetic repulsion trying to blow protons apart. Standard nuclear theory treated the strong force's strength as a fixed input, something you measured and plugged into equations. With no particular reason to expect it sat anywhere special on the range of numbers it could have taken. As researchers modeled what would happen if that strength were adjusted even slightly, the results didn't degrade gradually. They broke. In papers synthesized later by researchers including Craig Hogan at the University of Washington. Published in his 2000 review, Why the Universe is Just So in Reviews of Modern Physics, the calculations showed that if the strong force were even 2 to 3% stronger, protons would fuse too easily, hydrogen would have burned up in the earliest moments of the universe, and no long-lived stars capable of stable fusion over billions of years could exist. A few percent weaker, and deuterium, the essential intermediate step in stellar fusion, falls apart before it can form, shutting down stellar nucleosynthesis entirely. Physicists proposed this window might be wider than calculated, and simply looked narrow due to modeling error. Refined nuclear models since the 1990s have only tightened the range further. Others suggested some deeper unified theory would eventually show the value was forced, not free. No such unified theory has produced that result. Every element heavier than helium in your body was cooked inside a star that could only exist because this single number landed inside a window a few percent wide. What decided that number never had the freedom to land anywhere else? And the moment carbon actually formed, the story gets stranger still. Number 6. Carbon's resonance coincidence. Fred Hoyle was not trying to solve a philosophical problem about existence. At the Cavendish Laboratory in the early 1950s, he was trying to solve a much narrower technical problem: how do stars manufacture carbon at all, given that fusing 3 helium-4 nuclei together simultaneously? The only route available is statistically almost impossible? Standard nuclear physics of the time predicted this triple alpha process should be so vanishingly rare that stars shouldn't produce anywhere near the carbon abundance actually observed in the universe, including the carbon inside every living thing. Hoyle worked backward from the fact that carbon obviously does exist in abundance and made an audacious prediction. Carbon-12 must have an excited nuclear energy state, a resonance, at almost exactly the right energy to make the triple alpha process dramatically more likely than plain probability allowed. In 1953, Hoyle predicted this resonance should sit at approximately 7, 65 million electron volts above the ground state of carbon-12. Ward Whaling's team at the Kellogg Radiation Laboratory at Caltech went looking for it that same year, and found it at almost exactly the energy Hoyle specified. Physicists tried to explain the coincidence as Hoyle simply making an educated guess that happened to land close. But the resonance had to fall within an extremely narrow energy band to work at all. And it did. Others noted oxygen's own resonance sits just below the threshold needed to convert all the carbon into oxygen, an equally narrow miss in the opposite direction, compounding the coincidence rather than resolving it. Hoyle himself later said the case looked to him like a put-up job. Language most physicists avoid, spoken by the man who did the calculation. Every carbon atom in your bloodstream exists because two separate nuclear resonances landed in two separate narrow windows. Was that arrangement predicted by deeper physics, or simply found, the way you find a key that happens to fit a lock nobody built? That single coincidence sits inside a far larger one. Number 5. The Anthropic Principle's two camps. Brandon Carter was attending the 1973 International Astronomical Union Symposium in Poland, commemorating Copernicus, where the working assumption of 4 centuries of astronomy was being celebrated, that humanity occupies no special place in the cosmos, the Copernican principle, that Earth and its observers are unremarkable. Carter stood up and challenged the room. He argued that observers, wherever they exist, can only ever measure conditions compatible with their own existence, so certain features of the universe that look special are special only in the narrow sense that they're the only features an observer could ever be around to measure. In his 1974 paper Large Number Coincidences and the Anthropic Principle in Cosmology, Carter split this insight into 2 distinct claims that physicists still argue over today. The weak anthropic principle says observed values of physical constants are constrained by the requirement that observers exist to observe them, an uncontroversial statement of selection bias. The strong anthropic principle goes further, suggesting the universe must have properties allowing life to develop, a claim some physicists read as implying purpose, and others reject as untestable metaphysics dressed as physics. John Barrow and Frank Tipler expanded the argument into a full 1986 book, The Anthropic Cosmological Principle, and drew sharp criticism from physicists including Martin Gardner, who argued the strong version was unfalsifiable and therefore not physics at all. The disagreement has never been resolved because the 2 camps are answering different questions with the same data. The weak principle tells you why you can only measure certain values. Neither version tells you why those values were available to be measured in the first place. One escape route from that question rewrites the scale of reality itself. Number 4. Multiverse as the non-design escape. Steven Weinberg was working on supersymmetric field theories at the University of Texas at Austin in the 1980s. Trying to find a symmetry principle that would force the cosmological constant to 0 and make the fine-tuning problem disappear through pure mathematics. Every attempt failed. Standard field theory predicted the vacuum energy of empty space should be enormous, roughly 120 orders of magnitude larger than what astronomers could observe. And no symmetry Weinberg or anyone else could construct brought that number down without breaking something else. Rather than force the constant to 0, Weinberg flipped the problem. In his 1987 paper Anthropic Bound on the Cosmological Constant, published in Physical Review Letters, he calculated that if the cosmological constant varied randomly across a vast ensemble of separate universes, only those landing within a specific narrow range would ever form galaxies, and therefore observers, meaning the observed value wasn't fine-tuned by any mechanism, just selected for. The way only certain lottery tickets get looked at because only they won. Weinberg's predicted range was later found to be roughly consistent with the accelerating expansion discovered in 1998. Critics, including physicist Lee Smolin, argued the multiverse solution isn't falsifiable, since no experiment can currently detect a universe outside our own. Which means it explains the fine-tuning by asserting an unobservable structure exists to explain it. Others countered that string theory's landscape of an estimated 10 to the 500th power possible vacuum states gives the multiverse a plausible physical origin, not just a philosophical patch. Nobody has found a way to test which side is right. If the multiverse is real, uncountable versions of physics exist that never produced a single observer to notice they'd failed. If it isn't, the number that makes your existence possible had nowhere else it could have hidden. Nowhere the maths runs cold faster than the very beginning. Number 3. Roger Penrose's improbability estimate. Roger Penrose was studying the second law of thermodynamics and the arrow of time at Oxford, trying to understand a basic asymmetry. Why does entropy, the universe's disorder, only ever increase when the underlying laws of physics work the same forwards and backwards in time? Standard cosmology assumed the early universe's low entropy was simply a starting condition, unremarkable, one setting among countless equally likely settings the universe could have begun in. Penrose actually tried to calculate how likely that starting condition was compared to the alternatives, using the geometry of phase space to weigh every possible configuration the early universe could have had. The number that came out wasn't small. It was almost incomprehensibly small. In his analysis, published across several works including his 2004 book The Road to Reality, Penrose calculated the odds of our universe's specific low-entropy starting condition, driven mainly by the extraordinary smoothness of the gravitational field at the Big Bang, at roughly 1 in 10 to the power of 10 to the 123rd power. A number so large that writing out its digits would require more space than exists inside the observable universe. Physicists proposed inflation might account for the low entropy automatically. Penrose himself directly disputed this, arguing inflation requires an even more special starting condition to get going, making the problem worse rather than solved. Others suggested the calculation depends too heavily on choices about how to measure phase space volume and shouldn't be taken as a literal probability. The debate over the measure problem in cosmology remains unresolved among specialists. Every structured moment of your life, every memory that only runs in one direction, traces back to an initial condition rarer than any number your mind can meaningfully hold. What selected that one configuration out of a number of alternatives too large to write down? Every entry on this list ends in the same room. Number 2. The cosmological constant problem. Steven Weinberg, alongside a generation of theoretical physicists working through the 1970s and 80s, was trying to reconcile quantum field theory's prediction for the energy density of empty space with what cosmologists could actually measure. Standard quantum field theory predicts that empty space isn't truly empty. It seethes with virtual particles popping in and out of existence, and summing their contributions gives vacuum energy a specific, calculable, enormous value. One theorist's expected observation would roughly confirm. It didn't confirm it. It missed it by more than any prediction in the history of physics has ever missed anything. In his landmark 1989 paper, The Cosmological Constant Problem, published in Reviews of Modern Physics, Weinberg laid out the full scale of the discrepancy. The observed value of the cosmological constant is smaller than the naive theoretical prediction, by a factor of roughly 10 to the 120th power. A mismatch physicists have since called the worst prediction in the history of science. Every attempted fix ran into a wall. Supersymmetry was proposed to cancel the vacuum energy terms against each other. Even in its most optimistic form, it only closes part of the gap, and no supersymmetric partner particles have ever been detected at the energies where they were expected. String theory was proposed to eventually derive the correct value from first principles, decades later. It produces a landscape of possible values instead of a single answer. Weinberg's own anthropic argument offers a selection explanation, not a mechanistic one. If the vacuum energy were only slightly larger, space would have torn itself apart before galaxies, stars, or you could ever form. The number that permits your existence is off from theoretical prediction by 120 orders of magnitude. And nobody has produced a calculation that lands anywhere close to correct. Which brings this list to the only place it can end. Number 1. The question physics can't settle. Every physicist named on this list set out to answer a narrow, technical, mundane question. Guth wanted to explain missing monopolies. Hoyle wanted to explain stellar carbon output. Weinberg wanted a symmetry to force a number to zero. None of them set out looking for fine-tuning. Standard practice in physics treats constants as inputs you measure, not questions you interrogate. A value is a value. Full stop. With no expectation that why this number and not another is even a question physics is equipped to answer. And that's exactly where every entry on this list has stalled. Physicist Sean Carroll and others have pointed out that fine-tuning arguments run into a structural wall. to calculate how improbable a constant's value is. You need a probability distribution over all the values it could have taken, and no such distribution can currently be derived from physics itself. You need a theory that stands outside our universe's laws to generate it, which is precisely the theory nobody has. The two camps from Carter's 1974 split have not moved an inch closer in 50 years. One side treats the fine-tuning as evidence of design or selection across a real multiverse. The other insists it's an artifact of asking a malformed question, akin to asking why a coin that landed heads had to land heads. Both camps agree on every number. They disagree entirely on what the numbers mean, and neither side has found an experiment that could settle it. That disagreement isn't a gap waiting for more data. It's the edge of what physics, as a method built on testable predictions, can currently reach. The universe is not confused about its own constants. Every equation on this list runs perfectly, checks out under every experiment ever devised, and describes reality with a precision that borders on unsettling. We are the ones left holding numbers we can measure but cannot derive, watching every anomaly on this list sit not at some distant edge of unfinished science, but dead center of our most rigorously tested theories. That is the part that should keep you up. Not that physics has holes, but that it has none. And the fine-tuning is still standing there anyway. If you want to see more videos like this, click the video on screen now.